This is the 5th video in the IPC series on surface mount solder joint evaluation. In this tape, we're going to be examining J-lead surface mount components. J-lead components come in different sizes and shapes. Some have a dozen or more leads. Some have well over 100. The J-lead looks like a small fishhook, with the end of the lead curved underneath the component package. While there are several types of two-sided J-lead components, J-lead components will typically have leads on all 4 sides of the component package. One of the advantages of a J-lead over the gull-wing leaded style is the reduced amount of space required for mounting the component. Since most of the J-lead is underneath the component package, it takes up less overall space on the board. This allows for higher component density on the assembly. The solder connections on J-lead components take up about as much space as a leadless connection. But J-lead components have an advantage over leadless components because of the flexibility or compliancy provided by the component leads. A leadless component is connected to the board by a solder fillet. The solder fills in the space between the land on the board and the castellations, or metallized terminations, on the component. Whenever the assembly is powered up, the board will expand faster than the leadless ceramic component. As the product is powered down, the assembly will cool. Over a number of cycles, the solder may eventually fail from this repeated stress. The J-leads are designed to add flexibility to the solder connection. When either the component or the board heats up and expands, the lead absorbs the tension by bending slightly. This stress relief feature of the J-lead improves the long-term reliability of the solder connections. The difficulty in inspecting the entire J-lead solder joint is perhaps the main disadvantage of this particular style of component. The solder that joins the J-lead and the land together is readily visible on the outside edge, or heel of the joint. This is the most important part of the solder connection, since this is where the stress from expansion and contraction is concentrated. The component body and the heel of the lead tend to hide the toe, which curves underneath the component. This makes it difficult to see the entire solder joint. When it is important to see the entire solder connection, X-ray equipment can perform this function. The X-ray machine can look down through the top of the component and display a 2-dimensional image of each of the J-lead solder joints. On this particular machine, the various shades of gray indicate the thickness or vertical height of the solder. If you tilt the board sideways and watch the black and white image on the monitor, you'll see how the gray color changes. The interpretation of X-ray images requires additional training, but you can see how this type of equipment can be a valuable inspection aid. X-ray technology is also used when the electrical test system indicates a problem with a particular lead. In this case, the absence of dark spots where the heel and toe fillet should appear indicates that the lead may not be even or coplanar with the other leads. You might remember coplanarity from the previous video in this series. An evenly colored solder joint can indicate that the lead is not contacting the land in the same plane or level as the other leads. This generally indicates a weak solder joint or no connection at all. X-ray inspection is typically done on a scheduled basis to ensure that nothing has changed in the process. X-ray can also be useful in setting up or qualifying new production runs and for inspecting lead-to-land alignment. For most applications, it's unnecessary to visually inspect every solder joint, but it is important to know what a proper J-lead solder joint should look like in order to make sure that the assembly process is in control. The easiest way to visually inspect a J-lead connection is at the 4 corners of the component. If you tilt the board sideways, you'll see a side view of the solder joint. From this angle, you can inspect the heel of the solder joint, where the lead starts to bend over the land. The solder should feather smoothly onto both the lead and the land. The heel fillet should also have a concave or inward curve. The angle that the solder contacts the lead and the land indicates the amount of attraction or wetting between the solder and the metals that are being joined. The lower the contact angle, the better the wetting characteristics of both the lead and the land. If the solder contact angle increases, this indicates that the wetting or solder adhesion has decreased. A 90-degree contact angle is where the solder leaves the land or the lead at a right angle, or at a perfect square. A contact angle in excess of 90 degrees is allowed, as long as the solder fillet extends all the way to the edge of the land. A solder joint with excess solder will look something like this. When the solder fillet does not begin at the edge of the land, and the contact angle exceeds 90 degrees, this is an indication of improper wetting. This condition is not acceptable. The front view of the heel is the most visible part of a J-lead solder joint. Here we see the slightly tapered side fillets, feathering toward the outside edges of the land. The solder contact angle should also be the same along these side fillets. Side fillets are not required for any class of J-lead solder joints, although they are preferred. Now let's look at the end of the component lead, or toe. Typically, the toe won't be covered with solder, since it usually sticks up higher than the solder fillet. This is perfectly normal. The solder fillet at the toe of the lead should resemble the heel fillet. The contact angles should be similar if the lead is properly centered over the land. Later on during this videotape, we'll be defining minimum solder fillet conditions that are caused by lead-to-land misalignment. Another thing you can easily see on any solder joint is the texture of the solder. Every solder joint on the entire assembly should have a similar texture. If one or two solder joints are discolored or excessively grainy, this may be an indication of contamination. This is not a desirable condition. In this case, you need to take corrective action to prevent further occurrences. Make sure that your supervisor is informed quickly so that the source of the problem is eliminated. Another condition involving solder texture is voids and blowholes. These particular types of defects are usually caused by excess moisture, solvents in the solder paste, or an improper temperature profile during the solder reflow operation. The volume of solder in the joint is another major concern. If there is not enough solder, the joint may not be able to absorb the stress of expansion and contraction over the life of the assembly. A cracked solder joint may cause the product to fail. Excessive solder can also create a problem. If the solder wicks up between the lead and the package body, the lead won't be able to bend in order to absorb the expansion of the component. Again, the potential for solder cracking would be increased. Excess solder can also cause cracking of the component package. When the solder touching the underside of the component heats up, it will actually grow slightly and press up on the body of the component. Cracks in the component body can result. If moisture is allowed to enter the package, this can eventually result in an electrical malfunction. In the next section, we're going to be reviewing the maximum and minimum solder fillet sizes and the lead-to-land alignment criteria from the Joint Industry Standard ANSI J Standard 001. But let's stop now to review the information we just covered and to answer any questions you might have before we continue. Now we will review each of the dimensional requirements from the J Standard 001. Table 9-4 provides the boundaries for lead-to-land misalignment and solder fillet sizes for all types of J-leaded components. Before we review these dimensions, we need to point out that you are not expected to measure every solder joint to see if it meets these requirements. When the variation is extreme enough to fall below or exceed any of these minimum or maximum dimensions, then the condition should be easy to detect. The ANSI J Standard 001 requires corrective action when 0.3% or more of the solder joints exceed these control limits. Of course, it's not a good idea to have any solder joint close to minimum or maximum conditions. Consider these imperfect solder joints as an indication that your process needs corrective action rather than correcting each specific solder joint. It is also important to know exactly what the acceptance criteria are for the specific class of assemblies that you build. Your instructor may want to pause the tape after the discussion of each feature to make sure that you understand how to apply these acceptance requirements. The first feature we'll be discussing is the maximum side overhang, or dimension A. Side overhang is a relatively common condition. Occasionally, the leads won't line up precisely over the lands on the board. But how much side overhang is acceptable? For both Class 1 and Class 2 assemblies, the maximum side overhang is limited to 1/2 of the width of the component lead, or 1/2 of dimension W. If the lead extends more than halfway over the edge of the land, the solder joint would not be acceptable. Class 3 for high performance, high reliability assemblies allows only 1/4 or 25% of the lead to extend over the edge of the land. The next dimension in Table 9-4 is maximum toe overhang, or dimension B. None of the three classes have a specific measurement for toe overhang. As long as the solder joint meets all of the rest of the visual, dimensional, and fillet formation criteria, then toe overhang is allowed, provided minimum electrical spacing is not violated. The next feature is minimum end joint width, or dimension C. Note that the minimum end joint width is measured at the thinnest part of the solder joint. Typically, there will be a slightly concave fillet extending down toward both edges of the land. In this particular case, the thinnest part of the solder joint would be measured between the tops of the side fillets. Minimum end joint width really becomes important whenever the lead extends over the edge of the land, which we previously defined as dimension A. Class 1 does not have a specific measurement for minimum end joint width. As long as a properly wetted fillet exists and the side overhang is within the allowable limits, then the solder joint should be acceptable. Class 2 and 3 assemblies both have the same requirement, which is dimension W minus dimension A. This means that the solder joint needs to be at least as wide as the width of the lead, or dimension W, minus the allowable overhang, or dimension A. You may remember that Class 2 allows up to 1/2 the width of the component lead to extend over the edge of the land. If this overhang is at the maximum condition of 1/2 of dimension W, then we need to subtract 1/2 W from the width of the lead. The result is that 1/2 W, or half the width of the lead, is the minimum end joint width for Class 2. Class 3 allows only 1/4 of the lead to extend over the edge of the land. If we subtract 1/4 W from dimension W, we get 3/4 W, or 75% the width of the land as the minimum end joint width for Class 3 assemblies. The next requirement is the minimum side joint length, or dimension D. Notice that this particular measurement is made at the narrowest part of the solder joint. Usually this is from the top of the heel fillet to the top of the toe fillet. Class 1 does not have a specific measurement. The only requirement is a properly wetted fillet. Class 2 and 3 both require a minimum solder joint length of 1 1/2 times the width of the component lead. As an example, if the component lead measures 0.4 millimeters, then 1.5 times 0.4 millimeters equals 0.6 millimeters. 0.6 millimeters would then be the minimum side joint length for this particular lead width for either Class 2 or 3 assemblies. Maximum fillet height, or dimension E, requires that the solder fillet should not touch the body of the component for all three classes. This could restrict the flexibility of the lead and potentially damage the component package. Another requirement, minimum heel fillet, or dimension F, requires only a properly wetted fillet for Class 1. For Class 2 assemblies, the formula describing the minimum heel fillet is dimension G plus 1/2 of dimension T. Dimension G, or minimum solder thickness, is the height of the solder underneath the component lead, where the lead comes closest to the land. This height can vary depending on the amount of solder underneath the component lead. 1/2 of dimension T is the same as 1/2 the thickness of the component lead. If we add up dimension G plus 1/2 of dimension T, we get the minimum heel fillet height for Class 2 assemblies. Class 3 assemblies require a minimum heel fillet height of dimension G plus the entire thickness of the lead, or dimension T. The minimum height of the heel fillet will also control the allowable overhang at the heel of the lead. For example, as the heel of the component lead extends over the front edge of the land, the size of the heel fillet will continue to shrink. At some point, there won't be any fillet height at all, due to the shape of the curved lead touching the edge of the land. If the overhang of the lead reduces the heel fillet to less than these specified requirements, the solder joint will not be acceptable. Remember that the strength of a solder joint is largely determined by the minimum heel fillet, dimension F, and the volume of solder between the lead and the land, minimum solder thickness, or dimension G. And even though dimension G has no specific requirement for any class of assembly, a properly wetted fillet must still be evident. That's all the dimensional requirements from Table 9-4 of the ANSI J Standard 001. It's a lot to remember, so it might be helpful to keep a copy of the specification on hand in case you have any questions. Other useful IPC publications for the evaluation of surface mount solder joints include the IPC A610, which illustrates all of the J Standard 001 solder joint criteria. Also a desk reference manual, the DRM SMT, which includes a visual summary of the dimensional acceptability criteria and sample defect photographs based on J Standard and A610 specifications. This concludes the final video in the 5-part series on surface mount solder joint evaluation. Let's review now and make sure that you understand how to apply all these dimensional requirements for J-leads in your company's assemblies.